Caffeine. This is the world's most accepted mind-altering substance. The fuel of mornings. The drug we never call a drug. It slips into mugs and cans so casually that we forget what it really is. A finely tuned stimulant, engineered by nature and refined by habit. Inside your brain, a chemical called adenosine quietly builds up as the day goes on. Picture it like invisible sand collecting in an hourglass. The more sand there is, the heavier your eyelids feel. It's your brain's natural brake system, telling you to slow down. Caffeine doesn't remove that brake. It disguises itself. At a molecular level, caffeine looks almost identical to adenosine, close enough to fool your brain. When you take a sip, caffeine rushes in and occupies the adenosine receptors, sliding into place like a perfect decoy. But it never activates them. It just sits there, blocking the real signal from getting through. Your brain can no longer detect how tired it actually is. With the brakes jammed, everything else accelerates. Dopamine rises. Glutamate fires. Focus sharpens. The pituitary gland senses this sudden spike and assumes something is wrong. An emergency. Adrenaline is released. Heart rate climbs. Pupils widen. Muscles tense. Your body enters a mild fight-or-flight state, just to read emails or sit in traffic. Here's the twist. You're not creating energy. You're borrowing it. Running emergency systems during a normal day. And there's another layer most people never hear. Caffeine wasn't made for us. It's a plant's chemical defense. A neurotoxin designed to paralyze and kill insects that try to eat the bean. We're simply large enough to survive the dose and interpret the warning signals as stimulation. That jittery edge, that's the toxin doing its job. And when the caffeine finally leaves your system, the illusion collapses. All that adenosine that kept piling up floods back in at once. The brake slams down. That sudden wave of exhaustion, that's the real cost of the energy you borrowed. So if caffeine is just the most socially acceptable stimulant on Earth, what happens when the drug isn't hiding in a coffee cup anymore? Nicotine. This is one of the most efficient delivery systems ever created for a stimulant. Fast, precise, ruthless. When nicotine is inhaled, it vaporizes instantly. It spreads across the vast surface of the lungs and floods the bloodstream. From there, it reaches the brain in under 7 seconds. Faster than many injected drugs. That speed isn't accidental. It's the foundation of its grip. Like caffeine, nicotine works through impersonation. It mimics a neurotransmitter called acetylcholine, the master switch of the nervous system. This chemical controls muscle movement, attention, learning, memory, and alertness. It's everywhere. And nicotine knows exactly where to go. It slips into nicotinic acetylcholine receptors and floors the accelerator. Adrenaline surges. Heart rate rises. Blood pressure spikes. Your senses sharpen into a narrow, intense focus. That's the stimulant side. But then something strange happens. People say nicotine calms them. And they're not wrong. By hijacking these master receptors, nicotine also triggers a powerful dopamine release in the brain's reward center. Dopamine doesn't just create pleasure. It quiets mental noise. It produces satisfaction. For a moment, the world feels manageable. So nicotine becomes a paradox. A stimulant that feels like a sedative. The real danger begins quietly. The brain adapts. Faced with constant artificial stimulation, it dulls its own receptors, turning down their sensitivity. It also slows its natural production of acetylcholine and dopamine. Within weeks, your brain's normal state shifts. Focus drops. Mood sinks. Restlessness creeps in. Now you're not using nicotine to feel good. You're using it to feel normal. That craving isn't psychological weakness. It's a neurological deficit. A brain rewired to demand a chemical it no longer makes enough of on its own. And once a substance can redefine what normal feels like, what happens when the drug doesn't just stimulate the brain, but completely reshapes it? Alcohol. This may be the most misleading drug of all. We call it a depressant, a social lubricant, something harmless that just takes the edge off. In reality, alcohol is a chemical bulldozer. Ethanol is small enough to slip through the blood-brain barrier with ease. And once it's inside, it doesn't target one system. It disrupts everything at once. Its effects unfold in a two-part takeover. First, alcohol amplifies GABA, the brain's primary inhibitory neurotransmitter. GABA is the slow-down signal, the brake that keeps thoughts from spiraling into anxiety and overload. Alcohol binds to GABA receptors and supercharges them. It's like tapping the brakes and having them slam to the floor. The first system to go offline is the prefrontal cortex. Judgment softens. Inhibitions dissolve. Anxiety fades. You talk more. You feel bolder. This isn't confidence being added. It's self-control being removed. The internal supervisor has been sedated. At the same time, alcohol executes its second move. It blocks glutamate, the brain's main excitatory neurotransmitter. Glutamate is the go signal. With that signal muted, everything slows down. Thoughts drag. Speech slurs. Coordination collapses. Your brain's processing speed drops across the board. That warm, relaxed sensation spreading through your body? That's vasodilation. Blood vessels widen, sending warm blood to the skin. It feels comforting, but it's a lie. You're actually losing heat from your core, which is why severe intoxication can lead to hypothermia. The body feels warm while becoming dangerously cold. And when the alcohol finally leaves your system, the real price arrives. Your brain rebounds hard. Glutamate surges. GABA crashes. The result is anxiety, light sensitivity, sound sensitivity, and that hollow, panicked feeling people call hangover anxiety. Your nervous system overshoots in the opposite direction. So if alcohol doesn't relax the brain, only suppresses it, what happens when that suppression becomes a routine escape instead of an occasional indulgence? Cannabis. This drug plays by a different set of rules. It doesn't just hijack existing systems like caffeine or alcohol. It taps into something our science didn't even know existed until the 1990s, the endocannabinoid system. Think of the ECS as the brain's master regulator, a dimmer switch for neural activity. It doesn't create signals, it calms them. It tells overexcited neurons to slow down. It's the system that whispers, relax. Take it easy. Your body naturally produces its own cannabinoids. The most famous is anandamide, named after the Sanskrit word for bliss. This molecule rises after exercise, meditation, or moments of calm. It helps you forget, unwind, even enjoy food. THC, the main psychoactive chemical in cannabis, is an imposter. It mimics anandamide. It binds to the same CB1 receptors in the brain. But it's not delicate. It's clumsy and powerful, flooding the system and lingering for hours. It pushes the dimmer switch far further than your own body ever would. The effects? Unpredictable. In the hippocampus, short-term memory falters. Suddenly, what was I saying becomes the norm. In the hypothalamus, appetite surges, the infamous munchies. In the amygdala, emotional signals can soften, easing anxiety, or twist, sparking paranoia. Time seems to slow. Music feels richer. Laughter comes easier. Every sensation is filtered through the hijacked master regulator, leaving the brain processing the world in a distorted, unusual, and unforgettable way. So if cannabis rewires the dimmer switch of the brain, instead of simply pressing the accelerator or brake, what does that tell us about the delicate balance our nervous system maintains every day? Cocaine. This is pure, unrestrained stimulation. A drug that doesn't politely ask, it hijacks. Its target is the brain's dopamine system. Specifically, the dopamine transporter, or DAT, the off switch for pleasure and motivation. Normally, neurons release dopamine into the synapse, a tiny gap between cells. Dopamine binds to the next neuron, sending signals of reward, drive, and excitement. Then the DAT acts like a vacuum, sucking the dopamine back up, resetting the system. Balance is restored. Cocaine breaks that balance. It races into the synapse and jams the vacuum cleaner. Dopamine keeps piling up. The off switch is gone. The synapse floods. Every signal is repeated, amplified, relentless. This isn't a synthetic high. It's your brain's own reward circuitry trapped in a screaming feedback loop. The onset is explosive. Euphoria crashes over you. Confidence skyrockets. Energy surges. You feel unstoppable. Your sympathetic nervous system joins the party, adrenaline spikes. Heart pounds. Pupils dilate. Blood vessels constrict. Then comes the inevitable reversal. The brain, overwhelmed, pulls dopamine receptors away from the synapse. This is downregulation. The machinery that once responded to pleasure now struggles to function. When the cocaine fades, reality crashes back. Dopamine is depleted. Fewer receptors remain. The vibrant, euphoric world turns gray, hollow, and heavy. And your brain remembers only one solution: the substance that created the chaos in the first place. So if cocaine can hijack the very circuits that define motivation and reward, what does that tell us about the fragile balance our brain maintains every day? MDMA. Often mislabeled as a stimulant or psychedelic, MDMA belongs to its own class. An empathogen, a chemical that forces connection, empathy, and emotional openness. Its mechanism is one of the most unusual and intense in the drug world. Like cocaine, it targets the brain's transporters, the vacuum cleaners of neurotransmitters. But instead of just dopamine, MDMA focuses on serotonin, the molecule of mood, memory, and social connection. And it doesn't just block serotonin. It flips the system entirely. MDMA enters the neuron, flips a chemical switch, and forces the transporter to work in reverse. The neuron's entire store of serotonin is dumped into the synapse. This isn't a gentle flood. It's a chemical explosion. Simultaneously, it pushes dopamine and norepinephrine into overdrive. Energy surges. Euphoria peaks. Bliss overwhelms. The come-up can be anxious. Adrenaline fires first. Then the serotonin wave hits. Suddenly, the world feels perfect. Touch feels electric. Music has depth you've never noticed before. A profound, unconditional love for everyone, and everything spreads through you. This is the empathy effect. Serotonin dominates, while oxytocin, the trust and bonding hormone, amplifies it. But the come-down is unforgiving. You've emptied your brain's serotonin reserves. Rebuilding takes weeks. The days after MDMA are often marked by depression, emotional numbness, and strange brain zaps. Your mood-regulating system isn't just depleted. It's recovering from a chemical trauma. So if MDMA can turn your brain into a temporary paradise, what happens when that paradise vanishes, leaving only the emptiness behind? LSD, lysergic acid diethylamide, the king of classic psychedelics. A substance so potent its doses are measured in micrograms, millionths of a gram. One tiny molecule can topple the foundations of your reality. Its mechanism is as intricate as its effects are profound. LSD primarily targets the serotonin 2A receptor, known as 5-HT2A. It slips in, and the receptor folds over it, trapping the molecule inside. This is why a single trip can last 8 to 12 hours. The molecule is physically stuck, continuously stimulating the receptor. But what does that stimulation do? These receptors are most concentrated in the brain's default mode network, the DMN. The DMN is, in simple terms, you. Your ego. Your inner monologue. The part that dwells on the past, worries about the future, that whispers the self into existence. LSD shuts it down. By overstimulating these receptors, it dissolves the DMN. Your sense of self evaporates. This is ego death. With the central filter gone, the brain begins to rewire itself in real time. Regions that normally don't communicate, like the visual cortex and auditory cortex, start talking. Synesthesia emerges. You hear colors. You see sounds. The boundary between self and other blurs. You may feel united with the universe, not metaphorically, but because the neurological barrier defining you has been chemically erased. The trip isn't a hallucination in the traditional sense. It's a perception shift. You are seeing the raw, unfiltered input of your senses, processed through a brain temporarily stripped of its central operating system. So if LSD can dissolve the ego and scramble perception itself, what does that tell us about the fragile architecture of reality in our own minds? Ketamine, known as a dissociative anesthetic, a polite term for what is, in reality, a reality anesthetic. It doesn't just numb the body, it severs the mind's connection to the body. Its mechanism is unlike anything we've covered so far. Ketamine blocks NMDA receptors, the gateways for glutamate, your brain's main excitatory signal. Glutamate is the chemical that powers thought, processes information, and forms connections. Ketamine steps in and shuts the gates. A chemical information blockade. It's like cutting the fiber optic cable to your brain. Sensory signals, sight, sound, touch, still arrive, but they can't be properly processed. Your thoughts disconnect. Your mind loses its link to your body. This is dissociation. At low doses, it's floaty, dreamy, slightly drunk. At high doses, you enter the K-hole, a state of near total sensory deprivation. Your mind is untethered from reality, drifting in an internal void, unable to process the outside world. This is why ketamine became a battlefield anesthetic. Soldiers could remain conscious during surgery, yet feel no pain, and remember none of it. Its emerging use as an antidepressant is equally remarkable. By temporarily shutting down the brain's main ghost signal, ketamine disrupts rigid negative thought loops. This forced reboot allows the brain to rapidly form new, healthier connections in the absence of old patterns. So if ketamine can sever the mind from the body and reset neural circuits, what does that tell us about the fragile threads that tie our consciousness together? Opioids, heroin, morphine, fentanyl, oxycodone, the ultimate off switch for pain. They mimic your body's own natural painkillers, called endorphins, short for endogenous morphine. Your brain has a finely tuned pain regulation system. When you're injured, it releases endorphins that bind to opioid receptors, dulling the signal so you can function. Opioids are the molecular sledgehammer version of this system. They bind to the same mu-opioid receptors, but far more powerfully. Pain doesn't just fade, it disappears. And that's not all. This binding triggers a massive dopamine flood. Euphoria washes over you. A two-for-one effect. No pain, all pleasure. This is also what makes opioids so dangerous. Opioid receptors aren't confined to pain and pleasure centers. They're densely packed in the brainstem, the primitive lizard brain that controls survival functions. When opioids bind there, critical signals begin to shut down. Most dangerously, the drive to breathe is suppressed. The euphoric high lulls the user into bliss. But as the dose overwhelms the brainstem, the body simply forgets to breathe. No gasp, no panic, just silence. The high is so intoxicating it convinces even the most ancient part of your brain that survival is no longer necessary. So if opioids can simultaneously erase pain and override your deepest survival instincts, what does that say about the delicate balance between pleasure and life itself? Methamphetamine. If cocaine is a hammer, meth is a tactical nuke. It belongs to the same family as amphetamine, like Adderall, but one small chemical change, a methyl group, makes it far more potent. It crosses the blood-brain barrier faster, floods the brain more completely, and leaves a trail of chemical chaos in its wake. Meth targets the same dopamine and norepinephrine systems as cocaine, but its assault is threefold and brutal. First, block the vacuum. Like cocaine, it jams the dopamine and norepinephrine transporters, letting these chemicals pile up in the synapse. Second, reverse the vacuum. Like MDMA, it flips the transporters inside neurons, forcing even more dopamine out. Third, purge the stockpile. Meth invades the vesicles, the protected storage bubbles inside neurons, and empties them into the cytoplasm, which then floods the synapse. The result is a dopamine tsunami unlike anything else in the drug world. 12 hours of superhuman energy, razor-sharp focus, and intense euphoria. But the cost is devastating. This chemical onslaught is neurotoxic. It burns out nerve endings. The oxidative stress and metabolic strain physically destroy the terminals that release dopamine. This isn't simple downregulation. It's demolition. The brain doesn't just run low on dopamine. It can be permanently damaged. So if meth can ignite the brain like a supercharged engine, while simultaneously destroying the circuits that make thought and reward possible. What does that say about the limits of human neurochemistry? If you found this dive into the hidden science of drugs fascinating, hit that like button and subscribe to Strange Wise for more mind-bending explorations. Don't forget to turn on notifications so you never miss a journey into the strange, mysterious, and unexplained. Comment below which drug's effects shocked you the most. We love hearing your thoughts.